In this video, we're going to talk about trigonometric integrals. A trigonometric integral is an integral of a trigonometric function, or more usually a product of trigonometric functions. Oftentimes, such an integral can be evaluated using substitutions and trigonometric identities. So let's start with the following. If an integral has the form, so we're looking at an indefinite integral of a product of sine functions and cosine functions, but let's give it a power. Let's give it an exponent. Let's say n, and we're going to multiply it by cosine of x raised to another power. Let's say m, and we're integrating with respect to x. If an integral has this form, then it may be solved or evaluated using substitution and identities. The chief identity that we want to use is the Pythagorean identity. So let's write that down. So what does the Pythagorean identity tell us? It says that if you have sine x quantity squared plus cosine x quantity squared, that will always equal 1 regardless of what x is. What this allows us to do is change from sines to cosines or from cosines to sines, provided that you have a square there. So in other words, if you have any even exponent, you can do that. So remark, if we have an even exponent on sine x or cosine x, we can transform from sine to cosine, or the reverse, cosine to sine. Let's look at an example so we can be more precise about this. So if I have sine of x to the 6th power, so the exponent is even, then I can always write this as sine x quantity squared raised to the 3rd power. And then I can use the Pythagorean identity here. So this becomes 1 minus cosine quantity squared, all that raised to the 3. So we start with sines, and then we turn it into cosines. Notice that this is all raised to the 3rd power. So it's going to be a more complicated expression, but the idea is that you can get it all in terms of cosines. Now, you can only do that if you have an even number of them in your product. It also works the other way around. So if we start with cosine of x to, say, the 4th, then we can write that as sine, not sine, we can write that as cosine x quantity squared. So that becomes 1 minus sine x quantity squared, and all that raised to the 2nd power. So again, we're using the Pythagorean identity right there. Let's write it like that. That's where we're using the Pythagorean identity. So anytime you have an even product of sines, you convert them into cosines, and anytime you have an even product of cosines, you can convert them into sines. Why would any of this be helpful? Well, it'll make more sense if we just look at an example. So let's start with, say, this example. The integral of sine x to, let's just say, the 8th times cosine of x to the 5th dx, for example. Now, what is the objective here? The objective is to evaluate this indefinite integral. We certainly don't know how to do anything like this just off the top of our heads. That is to say, we probably haven't encountered anything like this before. The objective here is to eventually use a substitution. And the substitution that we want to use is u equals sine of x. We can do that because we have some sines. We have a bunch of them, actually. We have 8 of them. So this right here, this is u to the 8. The main issue is these cosine terms, but we can always get cosine in terms of sine as long as we have an even number of them. You might notice we actually have an odd number, but that actually is to our advantage, because if u is equal to sine of x, then du is the derivative sine, which is cosine of x, dx. So we need a cosine x to go with the dx here. So what I'm going to do is I'm just going to take one of these cosines out of the 5 and write it on its own. So we're going to have the integral of sine x raised to the 8 times cosine x. And like I said, I'm going to take away 1, so I'm going to leave 4 behind, and then I'm going to write that times cosine x dx. So sine x is u, so this is u to the 8. And cosine x dx, that's our du. In the middle here we have cosine x to the 4th. But, as we saw earlier, we can write cosine x to the 4th as an expression involving only sines. So I can take this cosine x to the 4th and rewrite it like that. So this is going to be the integral of sine x raised to the 8 times 1 minus sine x quantity squared, all raised to the 2, times cosine of x dx. Now, the first term hasn't changed, that's u to the 8, and this last term is still du, but now in the middle, everything's in terms of sines. So we have 1 minus u quantity squared, well, 1 minus u squared, and that quantity squared. So what our integral becomes is the integral of u to the 8 times 1 minus u squared quantity squared du. Now this isn't a trivial integral because you still have to square this term 1 minus u squared. So it's not trivial, but it's polynomial. It's something that we know how to do, and we can do it now. So we have a u to the 8 times, this is going to be 1 minus 2u squared plus u to the 4th du. And now you can use distribution. So this becomes u to the 8 minus 2u to the 10 plus u to the 12 du. And it's a polynomial, so we can repeatedly apply our product rule. So it's u to the 9th over 9 minus 2u to the 11th over 11 plus u to the 13th over 13 plus a constant. And then at some point we have to remember that u was equal to sine of x, and we have to plug that back in. U equals sine of x. You plug that back in, and what you're going to end up with is 1/9 times sine x raised to the 9 minus 2 over 11 times sine of x raised to the 11 plus 1 over 13 times sine x raised to the 13 plus a constant. So that is our answer. It's a complicated trigonometric expression, but it's something that we were able to do. We probably wouldn't have been able to do it directly just looking at our original integral, sine x to the 8 times cosine x to the 5. However, with a little careful use of trigonometric identities and substitution, we were able to do it. Now the key idea here, is that the power on the cosine term, on cosine of x, was odd. So if you look back at the integral here, let's include that much. So if you look back at the integral, the power on the cosine was odd, and that was important because we needed to strip away one of the cosines, and that cosine gave us our du. The fact that the power on the sine was even was irrelevant, because we if this was odd, if this was a 9, we would proceed in exactly the same way. So example, the integral sine x to the 9 times cosine x to, and we want to leave it as the fifth like it was before, dx, you can do the same thing. So again, you write this as sine x to the 9 times cosine x to the 4 cosine x dx. So you're able to strip away one of the cosines. You still let u be equal to sine, and then your du is cosine, and that's the important thing. Since your du was cosine, you needed a cosine x dx, which we have here. And nothing's changed about this term, except now it's u to the 9. And here we do exactly what we did before. You write that as cosine x squared, quantity squared. And then you use the Pythagorean identity. So this becomes 1 minus sine x squared, quantity squared. And that term is 1 minus u squared, quantity squared. So the important idea is that the power on the cosine was odd. Since power on cosine of x was odd, we could take one cosine of x term, or factor maybe, let's say factor, and use it for the du. But importantly, what was left behind was cosine of x raised to an even number. And because it was cosine x raised to an even number, you could convert this into sines. Convert into sine x terms. And that was the basic idea. So anytime you have an integral, if you have sine x raised to some number, which I think we were using n here, and then cosine x raised to m dx. So if m is odd, then write m. If it's an odd number, then it's going to be 2k plus 1. 2k is always even, so if you add 1 to it, it's always going to be odd. Then you have the integral sine x to the n, and then it's cosine x to the 2k plus 1 dx. And that's really what makes it work, because you have that extra plus 1 there, so you can strip that off, and you have the integral of sine x raised to the n times cosine x raised to the 2k times cosine x dx. And again, you let u be equal to sine of x, and then du is cosine of x dx. And so you have here, you have u to the n, and here you have du. And this term in the middle, you do exactly the same thing. You write this as cosine of x quantity squared, all that raised to the k, and then you write that as 1 minus sine x squared, and raise all that to the k. And what is that? That's just going to be 1 minus u squared, just like it has been all the time. So this term right here is 1 minus u squared raised to the k. And so now you have an integral that's u to the n times 1 minus u squared raised to the k du, which is polynomial. This is all, if you multiply this out, to get a polynomial. That's not a trivial thing to do, though, because it's 1 minus u squared to the k. Now that k might be a large number. It's got to be an integer, a whole positive whole number in this case, but it might be big, and so this might be a really difficult thing to actually compute, but the point is that you're capable of doing it. It gives us a way of taking an integral that we don't know how to do and showing us a way to do it, even though that way might actually be difficult. In this case, we were assuming that m was odd, but this would work just as well if the power on sine was odd. You just flip things around. So remark, if the power on sine x is odd. So in the first case, we were looking at m as being odd, and m is the power of cosine. So here we were looking if the power on cosine is odd. If the power on cosine is odd, you use u equals sine of x as your substitution. So if the power on sine x is odd, you just switch everything. So if the power on sine x is odd, let u be equal to cosine of x. And du is then minus sine of x dx. But then you proceed in the same way. So the integral of sine x n times cosine x to the m dx. So we're assuming that the power on sine of x is odd. So we assume n is odd. So that's this number right here. That's a little bit sloppy. Let me just rewrite. That's a little bit sloppy too. Let's just rewrite it like that. So if we assume that n is odd, then we write n equals 2k plus 1. Again, 2k is always even, so if you add 1 to it, it's always going to be odd. And then what do you have? You have the integral sine x raised to the 2k plus 1 times cosine x to the m dx. And now what we're going to do is we're going to strip away that one sign. So now it's going to be the integral sine x to the 2k times cosine x to the m times sine of x dx. And so now we let u be equal to not sine but cosine. And then du is minus sine of x dx. So u is cosine, so this term right here is going to be u to the m. This term right here isn't du, it's the opposite of du, because we have a minus sign there. So it's the opposite of du. And for this term, you do exactly the kind of thing that we did before. You write this as sine x squared to the k, which you then write as 1 minus cosine x squared, and raise all that to the k. And what is this? This is 1 minus u squared to the k. So it's exactly the same kind of thing. You end up with the integral of 1 minus u squared raised to the k times u to the m. And now it's not du, it's minus du, so we just put a minus in front. So again, we can do this. It might be tricky because, again, that k might be a large number, so it might involve a lot of expanding, multiplying. But the point is that we can actually do it. Let's do a simple example. So let's look where the numbers aren't so big. So we're going to look at the integral of, let's say, sine x. And the whole idea is that we want an odd exponent on here, so let's just pick 3. Keep the numbers a little small. Times cosine x, and let's make this one 4 dx. So what I want to do, since this power on sine is odd, I want to strip away one of those signs. So it's going to be sine x quantity squared times cosine x to the 4th, and I'm going to write that sign over here, sine of x dx. Okay. So that third sign, the odd sign out, that I'm writing right there. So we have 2 and just 1 on its own. That together gives us 3. So we're going to make the same substitution that we've been talking about, u equals cosine of x, and du equals minus sine of x dx. So again, this term right here is not du, it's the opposite of du. And this term right here is u to the 4th. And this term, well, since we picked the numbers to be small, this one actually is very convenient. It's 1 minus cosine x quantity squared, because it's just sine squared. So this term is 1 minus u squared. So 1 minus u squared times u to the fourth times a minus du. So I'm going to put the minus sign in front. But let's just keep in mind this minus sign is that minus sign. Okay, so this we can actually just multiply through. So it's going to be u to the 4 minus u to the 6 du equals, so now we integrate it, u to the 5 over 5 minus u to the 7 over 7, and then you just put a plus c at the end. Well, but don't forget u is equal to cosine of x. So we just plug that in. So we're going to have a minus, and this is going to be cosine x raised to the 5 over 5 minus, let's just write it as cosine x to the 7 over 7, like that, plus c. We can run the minus sign through. Minus 1/5 cosine x, and we're raising that to the 5th power. Minus and minus is plus. 1 over 7 cosine x. Raise that to the 7th power, plus c. And that's your answer. Now here we've done both of these problems always assuming that one of the exponents was odd. When I say both of these problems, I mean both of the examples that we looked at. Here was our first example. We had an odd power on the cosine, and we did another one like that, but we still had an odd power on the cosine. And now we've done one where the power was odd on the sine, somewhere around here. There we are. Now, if they're both odd, then it doesn't matter which substitution you make. You can do it either way. So remark, if the powers on both sine x and cosine x are odd on both of these, then you can use either substitution, and it's fine. If you look back at this last example, we used the substitution u as cosine of x, and it didn't matter what the exponent was on cosine, so I could have made this cosine x to the 5. This could have been a 5, for example, and then this term becomes u to the 5. Then I just multiply that through, and this would be u to the 5 minus u to the 7, and so on and so forth. So if I'm making the substitution u equals cosine of x, it doesn't actually matter whether that exponent is even or odd. Okay, well that sort of begs the question, what do you do if both powers are even? So what if both powers are even? So that is, you have the integral sine x, and I think we were raising this to the n power, and then we have cosine x raised to the m power dx. So what if n and m are both even? Well, you can't use the same technique, because you can't strip off, there's not an odd one out that's left over that you can strip off and use your du. So in this case, we make use of the half angle and double angle identities. So here's the ones that you generally use. So you might have something like sine x quantity squared is going to be 1/2 times 1 minus cosine of 2x. It's called a double angle identity because your angle goes from x to 2x. You've doubled the angle, so that's why it's a double angle. Then you have cosine of x quantity squared. That's 1/2 times 1 plus cosine 2x. The only difference here is the sign. It's minus for sine and plus for cosine. These are two double angle identities. Another one that you might want to use is cosine x sine x. This one is equal to 1/2 sine 2x. So again, these are all double angle identities. So these are all double, because you double the angle. Now, any one of these can give you a half angle identity if you just write it the other way around. So note, if we start with sine of 2x, 1/2, then that's going to be cosine x sine x. So I can just write this as sine of 2x equals 2 cosine x sine x. And so now I'm going from 2x to 1x, so this is a half angle identity. Oftentimes they write it in a different way, like where you'd let that be equal to theta, and then these would be theta over 2, but we don't need to do that. It's the same thing. So this version here is a half angle identity. And these can be very useful when both your power on sine and cosine are even. So as a simple example, again, we want to do these examples with smaller numbers, because otherwise it gets to be a little bit difficult just because of the computations involved. So let's say that we have sine x squared times cosine x quantity squared. Here both of the powers are even. So we can't use our first technique, but we can use these double angle identities. Now you might be tempted to use the double angle identities for sine squared and cosine squared, and you can do it that way, but it's a little bit faster if you use the cosine times sine one here. So we rewrite this as sine x times cosine x quantity squared dx. Now sine x times cosine x, as we have here, I've written cosine times sine, but it's the same. So this is going to be 1/2 sine of 2x. So this is the integral of 1/2 sine 2x, and we're going to raise that to the 2 power. So you can take out the 1/2, but you have to square it. So this is going to be 1/4 times the integral of sine of 2x quantity squared dx. And now we make use of this formula for sine x quantity squared, but now it's 2x, there's a 2x there. So this is going to be 1/4 times the integral sine of something quantity squared. So again, we're making use of that identity right there. So it's going to be 1/2 times 1 minus cosine times double the angle dx. Now this is 4x, because whatever angle you start with here, you double it. That's why it's called the double angle identity. So if you start with x, you double it to get 2x. Here I have 2x, so I double it to get 4x. Now if you prefer, you could think of this angle as being theta, and this angle as being 2 theta. And so you could just write theta for all of these, 2 theta, if you prefer. The point is that now we can actually do this. We can evaluate this. Let's take out that 1/2. So we're going to have 1/8 times the integral of 1 minus cosine 4x dx. So that's 1/8. And now we want to integrate 1, and that's just going to give us x. What about minus cosine? What's the antiderivative of cosine? Well, the antiderivative of cosine is going to be sine of 4x, but you have to divide by that 4. Think of it as the chain rule. The derivative of sine is cosine. So derivative of sine of 4x is cosine of 4x, but you have to take the 4 out. So there needs to be a 4 in the bottom for it to cancel with. So that gives us our answer, plus c. If you prefer, you can think of doing this with the substitution, and you let u be equal to 4x. u is equal to 4x, and then du is 4 dx. So this 4, you would need to put a 4 right in front of there. And so if you do that, you have to divide by 4, and that's where that 4 comes from. Another way to think about that is to say that dx is 1/4 du. And you can think, well, let's just plug that in there. And that's where that 1/4 then comes from. Anyway, this actually solves the problem for us. You could write it as x over 8 minus sine of 4x over 8 times 4, if you prefer. But there's your answer. And that's how you solve these problems that are products of sine and cosine, or powers of them. Similar techniques sometimes work if you have integrals involving tangents and secants. So note, some integrals of the form, so let's say the integral of, and let's have a tangent x raised to the n times the secant x raised to the m. So some integrals of this form can be evaluated in a similar way, but not always. The same sorts of techniques sometimes work, because there's also a Pythagorean identity for tangent and secant. In particular, what we know is we have the following identity. It's normally written more like this: 1 plus tangent x quantity squared is equal to secant x quantity squared. Now you might wonder where that comes from. It comes from the original Pythagorean identity. So if you have cosine x quantity squared plus sine x quantity squared equals 1, so this is the original Pythagorean identity, and if you divide everything by cosine quantity squared, then you have this new identity. I hesitate to call it new, but it's not the original identity, because cosine squared divided by cosine squared gives you 1, and then sine over cosine, that's your tangent, and they're both squared. And 1 over cosine is secant. So if you just take the original identity and divide by cosine quantity squared, you end up with this identity. And you can see that this tells you how to turn secants into tangents, or indeed, you can also, of course, work the other way and say that tangent x squared is equal to secant x quantity squared minus 1. Now, having an identity like this isn't really good enough on its own. You also need to have a similar relationship between the derivatives, and you do. The derivative of sine is cosine, derivative of cosine is negative sine. So when you compute the du for your substitution, you get the other function. You have something like that with tangent and secant, but it's not quite as nice. So we have the following derivative relationships. So if u is equal to tangent x, then du is not equal to secant, it's equal to secant squared. And if u is equal to secant, then du is not equal to tangent, it's equal to tangent times secant. So basically the idea is that you always do switch functions, but then you get an extra secant. See, when you differentiate secant, you get tangent, but also there's a secant there. And this is secant squared. So if you differentiate tangent, you get secant and a second secant. So that's why it's secant squared. So the same techniques that you had for sine and cosine won't work exactly, but some modification of them might work. For example, the integral of tangent x quantity cubed secant x quantity to the fourth dx. These types of problems are not always obvious how to proceed, and some of them there appears to be no way forward. This one we can do, and we can do it by looking at how many tangents we have and how many secants we have. The idea here is that if you let u be equal to tangent, you have to make sure that you have enough secants to be your du. So tangent is our u, so du is the derivative, which is secant x squared dx. Now fortunately there are enough of those. So what does that leave us with? That leaves us with tangent x cubed times, let's take away two of them, secant x squared times secant x squared dx. So I've taken two of those secants away from the 4. So we started with 4 secants, and now we have 2 here and 2 here. But I took away 2 to give me the du. So this is the du here. Now what's important here is that all of the remaining secants have to be even in number. So this is u cubed. So if you take away 2 secants, you need to still have an even number of secants because we're going to use this Pythagorean identity that's circled here. Because we have that secant x quantity squared, which is this term, secant x quantity squared, this thing is 1 plus tangent x quantity squared. And that is 1 plus u squared. So what do we end up with? We end up with the integral of u cubed times 1 plus u squared times du. And this is something that we can do. It's u cubed plus u to the 5th du, and this is something that we can evaluate. U to the 4 over 4 plus u to the 6 over 6 plus c, and then we just remind ourselves that u is tangent of x. And plug that back in. So you have 1/4 tangent x to the 4th plus 1/6 tangent x raised to the 6 plus c. So this sometimes works with tangents and secants, but it doesn't always, so that's something that you have to be wary of. Sometimes you can find an integral that's a product of tangents and secants and it just doesn't seem to be solvable, and indeed some of them don't have elementary antiderivatives that you can write in terms of well-known functions. Some of them, the best you can do is write the antiderivative as a definite integral.